Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 105, construct binary tree from preorder and inorder traversal. And I think this is a pretty good problem to do, and let's get into it. So given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree, construct and return the binary tree. And so the first thing we have to know is we have to know what an inorder and a preorder traversal means. So let's just draw out this tree. Okay. And so for the preorder traversal, so let's just call that P. The way it works is you go to the root, then you go to the left, then you go to the right node. So if you take a look, 3 is the root. We go to the left, that's 9. Now there's nothing else here, so we come back. We go to the right node. Once again, we go to this node, we take the root first, so 20. Then we go to the left, 15, and we go to the right, 7. We also have this inorder, so let's just say that's I, 9, 3. And so generally, you need both of these to make a tree. And let's just see how. So inorder goes left, right, root, right? So left 9, or sorry, left, root, right. So left, root. Now we're at this node. And as soon as we get to a new node, we have to do left, root, right again. So left, root, right. Okay, so typically when you have a preorder and you want to construct a tree from the preorder, what you want to do is you want to start at the left because that's your root. Okay? And if you have a post-order traversal, then your root's at the right. So what we're actually going to do is we're actually going to go node by node in this preorder, pop off nodes, and then see where they are in the inorder, and we could figure out where the bounds are for the left and right child. Because let's say we have this 3 node, that means we know that the left subtree is here and the right subtree is here. So we can simply give constraints for these. And then if there is no left or right subtree, like let's say we have this node, but our right constraint is over here, now the left is going to be like something like this, and then the right's going to be something like this, and now they're both going to be empty. So we can just have parameters for left and right constraints, and that's how we could figure out what's going to be part of the tree. So let's show what this would look like with an example, with this example. So let's say we don't have this tree. So the first thing we do is we go to the preorder and we get a node, right? So we have some function, we get a node, and we're going to pass in to that function. So actually, no, before we even do that, what we are going to do is we are going to make a function. So let's just call that some helper function h, and it's actually going to pass in the left and the right boundaries for the tree. So in the beginning, our left and our right is actually going to be over here, right? It's going to be the entire inorder array. So let's just say that's 0 and what is that? 1, 2, 3, 4. Okay. So we're going to pass that in. Now, every time we have a new node, what we're going to do is we're going to pop from the left. We can either pop or we can pass in a new index. Either one works, right? But let's just say we pop from the left and we declare that node to be the new node that we have. So we get into this function with this left being 0, this right being 4, and we're going to pop from the left. We're going to make a node. And then we're going to say, okay, now that we pop this, it's left node, and we're going to call recurse. So we're going to call this h again. And what we're going to do is we're going to think, where is the left subtree of this node 3? Well, this node 3 is at index 1, so the left subtree has to be from index 0 to index 0, right? The right index has to be 1 less than this, so the left has to be the same, and so that's the case. So it's index 0 to index 0. Okay, so now we recurse down, right? Then, because remember, for preorder, it's root left, right, so we get the root, now we do the left. And so we're in this new node, and so we pop again, get a 9. Now we try to go to the left. Well, this is 0, 0, so if we go to the left, how do we go to the left? We have to do right minus 1, right? because our node is at index 0, and so we'd have to take the original the index we're actually at, and then we'd have to subtract 1. So this would be h0 minus 1, right? And so here we have an invalid scenario where there is nothing between these two, and so this would just be an empty node. So just delete all this. So that's going to be something we're going to check for, is if the left is greater than the right, that means that we have an invalid node. So now we recurse back up to this 3, right? So we're here, and we try to make a right subtree. Well, okay, so we can do that. So for the right subtree, this node is at index 1. So for the right subtree, the left is going to go over here, right? And so this is going to be h of 2, and then whatever the right subtree used to be, which is, I think, 4. Yeah. Okay, so now we go over there. We're at this new node, h24, pop again. Okay, put in the 20. Now we try to go to the left of 20. Well, what's to the left of 20? So remember, when we go to the left, we just move the right over here. And so that's going to be h of, our left is currently at 2, and our right will also be at 2. So 2, 2. Okay, well, what's at index 2? That's just 15. That's the only number we have. So our left and our right are currently here. So we 15. And by the way, so we pop again. Now we try to go left. Well, to go left, we subtract 1 from the right. So to go left, we subtract 1. We make our right 1 less than the current node we're at. So whatever this index is, we make our right 1 less than that, right? Because that's the left subtree. It has to be somewhere over here. But now that we did that, our right is over here, and our left is greater than our right. So we'd have something like h2, 1, which is an invalid index again. So we're not going to do anything there. So like I said, we're going to have a check to make sure that the left is greater than or equal to the right. So we did that. Now we try to go to the right subtree, and our right subtree is going to be this left. So it's actually, sorry, so this gets deleted and we come back, and the left was here now. And so for the left was here now. So for our right subtree, the left is going to be 1 greater than whatever node we're at, right? For the right subtree, we do left equals index plus 1, and then for the left subtree, we do right equals index minus 1, and that makes sense because the left subtree has to be to the right of the current value we're at. So here this would be, so the index of 20 is 3, and our right was 4, so it's going to be 4, 4, right? Okay, we only have 1 node, so we pop this 7 again, and it's pretty easy to get the value for the node. We simply just check, do we have a valid index? Yes, we do. 4 is less than or equal to 4, so we just pop. We just keep popping from this until we have nothing left, or until we have no more recursion. Either way, I think they're going to be about the same time. But anyway, so technically we can say if there's nothing left, but actually what happens is when we try to recurse down to these left and right, we're going to have an error. So if we try to recurse down here, this node is at index 4. So remember, the left is the right minus 1, so that's going to be 4, 3, invalid. So there's nothing here. Now we can try to go over here, and this is going to be 5, 4, invalid as well, right? 5 is, 5, 4. So in both of these cases, the left is greater than the right, which means we have no subtree. Because the subtree in the array, right, you can only have it if left is equal to right, or if left is less than right. So left is over here somewhere else. But if left is greater than right, then there's nothing in between left and right, because it has to be left and then something and then right. So this would have nothing, this would have nothing, then we would just recurse back up and return. So hopefully that makes sense. We simply use the indices of where the node is at in this, and to get the actual value of the node, we just keep popping from the left of this. And if it was a post order, then we'd be popping from the right, because the root starts off on the right. And you just have to make sure that you have to recognize where to recurse. So if so this pre-order is root left, right, and so we need to get the value of the root, then we need to recurse left first. And post order is left, right, root. So this is left, right, root. And so in that case, we would have to go right first, I believe, right? Because we get the root, then we have to go right. So if you got this question as a post order, you would just get the right subtree first. So that's the only important thing there. Okay, so let's try to code that up. It's pretty straightforward. You just have to make sure you keep your pointers in the right spot. So first of all, what we want to do ideally is we probably want to change our preorder into a different data structure, because even though it's only 3,000 items, you don't really want to be popping from the start of a list. Although we could pass in the index, let's just change this to a deck. That way we can just keep popping from the left. So now we're going to have a helper function. And we're going to have a left and a right. And remember, at first they're going to be initialized to the left and right boundary of Inorder, right? It's going to be the entire list. Root can be anywhere in this thing. So it's going to start as, so we're going to have left, right, but we're going to, when we call it, we're going to initialize it to the boundaries. Okay, so now what are we doing? So remember, first what we do is we say if left is greater than right, we can just return none because we have an invalid index. Otherwise, what we need to do is we need to make a node. So we can just say, call that root equals tree node. And then what does tree node take? It takes a value and a left and a right. And so the value, remember, is going to be preorder pop left. So we're going to pop the leftmost number from this preorder array. And then the left and the right for now we'll say is null. Okay. Now we also need to get the index of where this is in Inorder. So that's important. Now how do we do that actually in big O of one time ideally, otherwise we'd have an n squared solution. Let's think about that. How would we get the index? Can we get the index? Like we have a left and a, well, actually, I don't think it would be an n squared solution because, yeah, I don't think it would be an n squared solution because we're going to keep narrowing down our index. So like we'll have to search through the whole array here, but we're going to keep narrowing and narrowing and narrowing and narrowing down our index. So I don't think it's going to be an n squared solution. Plus this number is also pretty small, so we can have it a little bit inefficient. I think that's okay. I don't really see how we can get, yeah, I don't really see how we can get it in the Inorder. Like imagine we start in the beginning. How do we know where it is in this? I don't think we know for sure. Because in the preorder, it's always going to be at the start, but we can't know for sure. So I do think we have to look where it is in the Inorder. So what we have to do is we have to loop from left and right, and then we have to find the index. So I do think there's like an index of, some kind of index of function in Python. However, let's just get it manually. So let's just say for I in range left. So it's going to go from left to right plus 1. Now we do need index. So just make that 0 for now. If Inorder I equals, and I do think these values are unique. So root val, so this is what we want. Then we have index equals I, and we can just break there. Okay, cool. So now that we know the index of where our actual node is in the Inorder, now it's pretty straightforward. So now we just do this. So now we just do root.left equals, we recurse down, right, helper. So remember we have this index. So remember for the root, for the left, it's going to be index -1. I know, sorry, no, it's not. It's going to be left and then index -1, right? So like, let's say our root is here, for example, and our left is here. Our left will stay that value, but our right needs to be index -1 because that's our like subsection we're searching. So that's going to be that. Now root.right equals helper. And remember, this is left +1 index. This is not index, this is right. Then we just return the root. And that should be all the recursion we need, I believe. Okay, so let's try this. So we just have to return helper 0 length Inorder one to start off because it can be anything. Yeah. Ooh, that's a problem. So I don't think, I am kind of interested. I didn't think we can actually pop from an empty deck with our logic. I thought that we would always just have null nodes if that's the case, but let's just make sure here. So 3 plus 3 node, preorder pop left. I mean, technically we don't need a pop left, but we'll still go out of bounds if we have an index, so I don't think that'll matter. Index equals 0. For ion range, if in order, so there's definitely going to be a, this should always find something for sure, I believe. Yeah. Yeah. Left, index, that seems fine. Yeah. Okay. So let's actually print some stuff just in case. So let's print left, right, and let's also print preorder. Let's just see here. Okay, so it's not even, so we clearly just screwed something up here, I think. Maybe I just like initialized the deck wrong or something. Let's just return none for now. Okay, so that's fine. And how in the world are we, how in the world is it not printing anything at all? That's interesting. Let's actually go back and print this. So I do think this will have a none, but this should still, yeah, here we go. Okay. Yep. Okay. So we pop the 3. Okay, so let's just see. So 0, 4, we pop the 3. Okay. Now we try to go left. Right? Yeah, we try to go left. And so then our index should be 0, 0. That's fine. Okay. And then we do have a left there, so we pop the 9. Okay. Now how do we get to the 0, negative 1? So let's see here. So our left and our right is 0, 0. Okay, so 0, negative 1 would just be a null node. Right. Now we would also go to 1, 0. Okay, which should also not pop, right? Now we go to 1, 4, which is the right node, I believe. Wait a minute. Ooh. We screwed something up. So this should not be left plus 1. This should be index plus 1. Because the index is where we made our node. Let's comment that out. See if we have any more errors. All right. So that was our slide error, is when we get the right, we have to take the index where we got the node, not the left plus 1. Okay, so then I did calculate it correctly. We do pop through the entire preorder while we go through this. Okay, so let's think of it, the time and space complexity here. So we do have to find where n is in Inorder, and we do a little bit of repeated work, right? Because like first we have to check this entire Inorder. Actually, I think I have a better idea actually, to save us some time. Yeah. Let's, yeah, I do think we have a better idea. So instead of, yeah, definitely, right? So I think what we can do, how big is Inorder? Inorder is preorder length, so it's 3,000 elements. Okay. But then we'd have to have, I think that's still better. Yeah. So I think what we can actually do is we can make a dictionary, and then we're not searching through where all these numbers are because they are unique. that would give us log n space, but technically I think our helper function can already recurse down to log n, or sorry, give us n complexity space, but then our helper function can already go down to worst case n complexity space, because we can have, once again, we can just have a tree of this, right, where we're just recursing all the way down, something like that. And so let's actually do that. So let's just have like locations maybe, and then we'll change the code a little bit, and then we should have better time complexity, I believe. So let's just say this is default get, and then for I v enumerate in order locations v equals I. So now we don't actually have to do the search thing. We can just say index equals locations dot val. Okay, let's try that code now. Cool. Okay, and so that worked, and I think we actually did do a little better actually. But so, yeah. So now let's do our time and space complexity. So now we can get the so we can get the index of our node in big O of 1 time, and our helper function can recurse down all the way, like I showed in this picture, to something like this. So this would still be big O of n, worst case scenario, if we do have a recursive stack frame that goes all the way down n nodes. That can technically happen, I believe. Yeah. So what would that actually look like, by the way, in our in order? So it would be something like, yeah, let's just see. So if we had something like, right, 1, 2, 3, 4, 5, 6. Yeah. Like this is a binary tree, but it doesn't have to necessarily be a binary search tree. So if this was our in order and our root was 1, and then our, whatever our preorder would look like something different, but whatever, this would give you a root of like this. And so here we'd have to go all the way down, and we'd have to go all the way down, and we'd have to hold this whole stack frame. So that's the worst case scenario here, in which case that would be big O of n, where n is the number of nodes we have. So let's think of the space complexity here. Oh, and by the way, so actually, even not even counting the stack frame, we are making n tree nodes, right? So if we're making, that would be for space though. So okay, so let's just think about the space. Yeah, but we do have to visit every node for time regardless. And so yeah, that's going to be big O of n. I think actually space is going to go to the recursive part, but yeah, time n, we do have to go for every single node in order. So that's going to be n space. So this is actually relating to the space, is this recursive stack frame. However, we also do have to make every single node. So I think it's big O of n regardless. So we do have to make every single node here. And so making this dictionary doesn't actually cost us anything in big O of complexity, because we already have n nodes. And so this is going to be n size as well, which is totally fine. Okay, so I think this is the answer for this. It's going to be big O of n and big O of n. So hopefully you like this problem. I definitely think it's a good problem to learn how to make trees, and I think it's a reasonably common problem for trees. You're going to have some other problems. Maybe not, instead of constructing a tree, you might have to like construct all trees or things like that. So I think this is definitely a good one to practice, and hopefully you like this one. And if you did, please like and subscribe to the channel, and I'll see you in the next video. Thanks for watching.